Hello everybody again. Um, Today we are going to do an experiment on the thin film interference. You already have seen the lecture, so you're familiar with it, but I'm going to kind of go over it very quickly. So if you have a thin film, and let's say you have a monochromatic light, namely a light with a single frequency, a laser light basically, and you shine that on the top surface of this thin film. Some of the rays are going to reflect, look at these rays. Some of them are going to pass through, and I'm considering that this thin film is transparent. So some of it is going to pass through and hit the other surface, the bottom surface of the thin film. And some right there, again, some of it will pass through, that we are not worrying about that, but some of it will reflect. So I drew this so that you see that the angle of reflection is the same as the angle of incidence here as well as here. And so this reflected light passes through the thin film and is going to come back into the air. We're assuming this is the air in here, or it could be any other environment, doesn't matter. And so it comes out and it is going to refract. Now the way I drew it, I am assuming that this is air, and this is some material with higher index of refraction. So you see that the way I drew it, the ray which is refracting is going away from the normal. Now these two rays are going to interfere with each other. They come to the eyes of the observer, and depending on how much is this thickness, they are going to have a phase difference between them. So this ray, or this set of rays, and this set of rays, they are going to have to interfere with each other, but they will have a phase difference. Depending on the phase difference, then excuse me, we can have either a constructive interference or a destructive interference. If the thickness is constant, like in this example, again, depending on what is this thickness and what is the wavelengths of this laser, the interference is going to result in either a constructive interference, in which you will see a bright fringe or bright line or area, or it's going to end up with a destructive interference, in which case you are going to see a dark fringe. However, in our experiment today, which I have shown again in here, this is a bit different. That was just the introduction, but this is the actual experiment that we are going to do today. We have our thin film in here is in the shape of a wedge, and you will see why. I've explained that in the lecture time by now. You already have seen it, but I'm going to explain it again. So we have a wedge-shaped thin film. Our thin film is actually air. And above that thin film, we have a plate of glass, which you're going to see later on. And below that is also you have a plate of glass. So this is very different from this case when you had your thin film being optically thicker. Here your thin film is optically thinner than the above and below medium. Okay, and by the way, as you know, the index of refraction of air is about 1. All right, so why is it that we try to make a wedge-shaped thin film? It's because we want to get not just one light fringe or just one dark fringe, but a series of light and bright fringes or lines. And knowing that, the relationship, as I'm going to show you later on, for the dark fringes is 2 times T times N is equal to M times lambda, M being equal to 0, 1, 2, all the digits, like that. You will see that at this end of this wedge thin film, thickness is 0. You have glass here, glass plate here, and so that at that point, the thickness is 0. You plug in here 0, and you can find one of these numbers, in this case m equal to 0, that satisfies this equation. This equation, as I'm going to explain for you in just a minute, is the equation that gives you the position of dark fringes. Namely, this equation is valid when we have destructive interference. So, this works for this point as I just explained. At some other thickness, this is not going to work, this equation, but rather this equation will work. 2Tn is equal to m plus 1/2 times lambda. Again, m equal to 0, 1, 2, etc. And for this position next to this dark fringe, you are going to get a different thickness, and that different thickness is going to satisfy this equation with some value of m. And therefore, this position is going to be corresponding to a bright fringe. And so on and so forth. This trend continues. So what you're going to get when you're looking as an observer from whatever that is coming back from the top and bottom surface of this thin film, you're going to get a series of dark, bright, and so on. And that's what I have shown in here. Now, obviously, the purpose of this experiment is to get familiar with this thin film interference. In order to make an experiment out of it, we are going to separate this side of the two plates, basically the maximum thickness of this wedge, by a piece of hair, or you can just put a piece of paper or anything else. Measure this ahead of time, which we have done, and you are going to see it yourself. And therefore, now we have a geometry that we can use in order to find the thickness of that hair or whatever piece of paper you put in there between the two glasses. And we can basically verify that all the equations that I've described for you are valid. So in order to get to that equation, let's look at this triangle in here, Q, P, Q, R. Now, first let me explain that what we have done. We have measured first the length of this wedge shape air between where the hair is to the beginning of where the two plates they intercept. And so this is the length of this whole part. We also have, as you're going to see, we have made a 1 centimeter. This D in here is equal to 1 centimeter. 2 lines in here, we drew it on the paper. And we can actually look at these fringes in here and find how many dark fringes exist between this point and this point. Now, these 2 points are kind of arbitrary, but the distance between them must be 1 centimeter, or it could be any other number, but we chose that this would be 1 centimeter. This D is going to show up later on, excuse me, in this equation. So, let's look at this triangle PQR and this bigger triangle in here, which is between, let's say, this point A, this point in here B, and this point in here C. These two triangles are similar, and so I can write the ratio of QR right here. Now I can take a look at this equation. QR over RP, which is really just this D1 centimeter, is equal to the ratio of this side of the bigger triangle T over this side of the bigger triangle L, right there. Now we have measured L and its uncertainty. We also have measured D and its uncertainty. QR, of course, is very difficult to measure, but we can determine it in other ways, and that's right in here. So if you look at this triangle from Q to, let's say, this point, let's call it Q prime, that is the thickness of the wedge at this point, at the end of this 1 centimeter mark. Okay, that's this thickness from here to here. And as far as this thickness is concerned, this is the thickness of the wedge at the beginning of this 1 centimeter mark. Okay, we don't have to measure this, we can calculate it. So if we want to find QR to plug into this equation so we can do the rest of the calculation, I'm going to say QR is equal to this total QQ prime, which is equal to thickness at this location, at the location where we have the I plus N dark fringe, this much, minus this thickness in here, which is the location of the first dark that we see, dark fringe, of the ith dark fringe at this location. Remember, these are the two locations where we have marked, and so we can basically see the beginning, the first dark and the last dark fringe that is within this distance. Okay, Ti and Ti plus 1. If I plus N. You subtract these two from each other, you're going to get QR, and that's what I have written right in here. Now we can calculate by our equations what is the thickness of the wedge in here. And this is where one of these dark fringes occurred. That's what we are reading from here. You're looking at the last location, looking at the last fringe, dark fringe, and that would be our QQ prime, thickness of the thin air. Okay, so that is going to be this number. Where this number comes from? It comes from this equation, right? That gives you the location. I'm sorry, not this one, this other equation that I wrote somewhere right here. This equation, that's the location, I guess I wrote it in here, position of dark fringes. So I'm going to use this equation for the ith, as far as the thickness is concerned, namely this thickness of the wedge shape at this location and this location. At this location, it will be I plus N fringe, so the value of the thickness of the film there is going to be this much, and then this much. This Ti is going to be the thickness of the wedge at the other end, which is at this point. So subtract these two thickness, and you are going to get QR. Okay, and therefore, of course, you simplify this right-hand side, and that becomes N times lambda divided by 2N. N is the number of dark fringes or lines. We count them. That's part of our measurement. Lambda is the wavelengths of the laser that I'm going to give that to you. And N is the index of refraction of the thin film, which is 1, because it's air. So I have the right-hand side, and as far as the left-hand side is concerned, from this equation, this triangle that I explained for you earlier, QR becomes T times D, which is 1 centimeter. You're going to convert it into meter, of course, divide by L, which is the length of the whole wedge. And so from combination of these two, you can find T. That's the thickness right here of that hair. Based on, basically, this is what we do. Measurement in here. Lambda is given. L we gotta measure at the beginning, D at the beginning, and N is equal to 1, so you can find T. Once you found T, you are going to compare that number with the actual thickness of the hair that we have measured with micrometer, and you're going to see that. And ideally, these two numbers would be the same. By doing that, we are basically verifying that all these equations were correct. By the way, one thing that I forgot to mention to you earlier is that when there is no phase difference, phase difference between the two rays which are coming from here and here, from the two surfaces of the thin air. If there is no phase difference, then the equation that gives you the position of bright fringes, namely constructive interference, is going to be this one, this equation, and the position of the destructive interference, where the dark fringes are located, is going to be by this equation. However, in this experiment, because of the fact that down in here, at this lower interface, we have glass with higher index of refraction than air. This is optically thick compared to the thin film. When the ray reflects in here, and I can draw it right here again. So the ray comes in here. I'm going to draw it a different color. Let's say with green. So let's say that in general, a ray comes in here, and it is going into the glass like this, and then goes into the air. So it's going to go away from the normal, and so it's going to go, let's say, in that direction. It goes in here, and it's going to reflect at this bottom part of this wedge-shaped thin film. And as it comes out, it is going to go towards the normal, because this is glass again. So it's going to go in that direction, and then it's going to come out. And then here it's going to go away. So that's one of the path of this ray. The other path is that there is reflection right in here. And these are the two rays that comes to the eyes of the observer. Now, in here, when this ray is reflecting, as I've explained it for you during the lecture times, this boundary, basically in here, it corresponds to a optically thick environment compared to the thin film. So when it reflects, there's going to be a 180 degree or pi radian phase difference. And therefore, the location of these two equations are going to flip. So that's what I wrote in here. In this experiment, it is the other way around. Namely, this equation that would have given you the equation for position of constructive interference, now it's going to give you destructive interference. And that's why I have used this equation right in here when I was trying to derive for you the equation that you need. So that's basically it. The rest of it we are going to show you in pictures that Micham is going to take and is going to show it to you.